So now we enter into the world of probability. And one of the things that makes probability a little bit difficult is that some probability questions are almost intuitively obvious. Very often when I ask people, what's the probability of flipping heads, when you flip a fair coin, they'll usually say 50-50 or 50% or 1/2 or something like that. But there's other times, many other times, when the probability is not nearly so obvious to calculate. I overheard a couple of people talking about the lottery, and one of them said, "Oh, I think my chances of winning are 50%. And the other person said, "You're crazy. What are you talking about?" And the first person said, "Well, I either win or I don't. So chances are 1 out of 2. But I think we intuitively grasp how ridiculous that example is, because the two outcomes, winning and losing the lottery, are not equally likely outcomes. There's way more ways you can not win than there are ways that you can win. So the basic equation or formula or fraction that we'll use to calculate a probability is the number of ways that the event can happen, or the number of outcomes that lead to the event, divided by the total number of things that can happen. So in our coin tossing example, the total number of things that can happen when you toss a coin is 2. It's either heads or tails. The number of ways that heads can happen is 1. So the probability of heads is 1 out of 2. And so this notation here, P and then parentheses A, that almost looks like function notation, P of A, is read the probability of A, or the probability of event A. That's kind of conventional notation. Also, it's kind of conventional notation to use capital letters A, B, and C for a generic event. You'll see the A's and B's and C's in a lot of our formulas. Usually, you can express probability as a fraction, but I think it's more often expressed as a decimal number, and it's got to be a decimal number between 0 and 1. Very important. You cannot have an answer to probability that's bigger than 1. Suppose this fair coin's tossed 3 times, and we want to know the probability of getting 2 heads. So we need to start counting. How many total things can happen when you toss a coin 3 times? And how many ways can you get heads? So here's a listing of what I believe are all the possible outcomes. I think there's 8 possible outcomes, and I kind of enumerated them in a little bit of an organized fashion. First, this is the ways you can get all heads. There's different ways you can get 2 heads with 1 tail, 2 heads with 1 tail, 2 heads with 1 tail. There's different ways you can get 1 head with 2 tails, 1 head with 2 tails, 1 head with 2 tails, and then that's all tails. So there's 8 possible things that can happen, and you notice that of those 8 things that can happen, we have 1, 2, 3 that result in exactly 2 heads. So the probability of 2 heads is 3 out of 8. In a little bit bigger problem, if we don't want to list all of these out, in this case, we could have figured out that there would be 8 possible things that could happen, the denominator of this fraction, by just doing 2 to the 3rd power. There's 2 different outcomes on the first toss, 2 different outcomes on the second toss, times 2 different outcomes on the third toss. 2 times 2 times 2 is 8. So there's a lot of probability that's done using this formula, or going back up here using this formula. A lot of probability that's done that way focuses on counting the total number of things that can happen and counting the number of ways that this event can happen. And that counting is sometimes referred to as combinatorics. This is the classical approach to probability, where you can count both the top and the bottom of that fraction. A lot of times, though, it's hard to count either the top or the bottom. So here's another interesting question that I saw in a stats book a long time ago. And it was this. If you toss a fair coin 10 times, what's the probability that somewhere in those 10 flips you see 3 heads in a row? And I think I originally saw this problem because people thought it would be kind of unlikely to see 3 heads in a row. Like they feel like that wouldn't be very random. So tossing a fair coin 10 times, there's 10 things that can happen on, 2 things that can happen on the first toss, 2 things that can happen on the second toss, and so on. So 2 times 2 times 2, 10 times. 2 to the 10th power is 1,024. So there's for sure 1,024 things that can happen. But this is going to be a long problem if I list all 1,024 things that can happen. By the way, I suppose I could list them. There's one of the 1,024 things that can happen. There's another one. There's another one. I could list all 1,024 things that can happen, but that would take a long time. And then I would have to go through the list and find how many of those 1,024 things resulted in heads, heads, heads somewhere. It turns out this problem is easier to do in Excel. And I had some people asking me about this that saw this on an earlier video. You don't have to understand anything I'm about to do in Excel. All you have to know is that I'm about to simulate this coin tossing problem. I'm going to simulate 0.507, 0.508, somewhere in that ballpark, I'm pretty sure is the probability. So the point is that computers are very fast now, and a lot of probability calculations are done using a simulation. Because I just did that simulation way faster than I could list all 1,024 things that can happen. But I'm pretty darn certain that the probability of heads, heads, heads is about 508. So that was just to illustrate the difference between figuring out probability via the classic approach as opposed to figuring out probability via simulation. Now, we were talking about ways of counting how many things can happen on top and how many things can happen on the bottom. Very important in that regard is permutations and combinations. But the mathematical symbol factorial appears in both formulas. So just a recap of factorial, when you see this exclamation mark, 5 factorial, that literally means to do 5 times 4 times 3 times 2 times 1. And so it doesn't really, the pattern doesn't really fall apart here. Most people are okay with 1 factorial being just 1, but it is kind of surprising to a lot of people that 0 factorial is 0. I mean, 0 factorial, it is a little bit surprising to some people that 0 factorial is 1. But the main reason why we need to know factorial is because it's used in 2 formulas. First of all, permutations. If I've got 5 items, like the letters A, B, C, D, E, and I want to choose 2 of them, and the order in which I choose them matters, meaning A, B, and BA are going to be counted as 2 different permutations, then the number of ways that this can be done is given by this formula here. Sometimes it's a capital P followed by a lowercase n and r. Sometimes the lowercase n is in front of the P, but it's always n factorial over n minus r factorial. So in this case, 5 factorial over 5 minus 2 factorial. The 5 is because there's 5 items to choose from, and the 2 is because we're selecting 2 of them. And anyway, 5 factorial over 3 factorial is 20, and that's the 20 things, the 20 possibilities we have listed here. So if we're selecting 2 letters from the letters A, B, C, D, E, and order does not matter, there's 20 ways that that can be done, and this formula spits that out. And before I go on, just wanted to mention that permutations are on the calculator. We press the math button, arrow over to the probability menu. Item number 2, that big capital P is for permutations. 5 items taken 2 at a time. And that'll tell me 20. So we've got a function on almost any kind of scientific calculator that'll do permutations. So there's really not any reason to know this formula. And again, sometimes the notation is like this instead of like this. Okay, then akin or similar to permutations is combinations. Let's say we have the same scenario, but now the order doesn't matter, meaning that we're not going to treat AB and BA as 2 separate groupings. So now, if I throw out the BA, because it's a duplicate of AB, and I throw out all the other duplicates, I end up with only 10 possible ways that you can select 2 letters. And that's given by this formula that also involves factorial. And if I plug in the numbers, we have 5 factorial over 2 factorial and 5 minus 2 factorial, and that'll all work out to be 10. And again, that's on the calculator. Math button, probability menu, item number 3, and 5 items taken 2 at a time is 10. And one of the disadvantages or one of the downfalls of the word combinations is that to a lay person who doesn't have any training in statistics, they would see this list of letters and they would see this list of letters, and they would say, a person with no training in statistics would say, oh, that's all the combinations of the letters A, B, C, D, E. But someone with some training in statistics would recognize that this is all the permutations, because A, B, and BA are listed as if they're different selections. This is all the permutations of the letters A, B, C, D, E taken 2 at a time. This is all the combinations of the letters A, B, C, D, E taken 2 at a time. And that's on the calculator. And it's also interesting to note, this comes up a lot more in a later chapter, that these combination numbers show up in Pascal's triangle. So, for example, if I do if I do 5 items taken 0 at a time, that's 1. If I do 5 items taken 1 at a time, let's type the number 1. If I do 5 items taken 1 at a time, that's 5. If I do 5 items taken 2 at a time, that's the one we already saw that was 10. If I have 5 items taken 3 at a time, that's also 10. And if I have 5 items taken 4 at a time, that's 5 again. And so these numbers 1, 5, 10, 10, 5, 1, that's just the numbers from one row of Pascal's triangle, if you're familiar with Pascal's triangle. So that's kind of an interesting little point there. So an example of how you would use combinations in a probability problem The original California lottery had 49 numbers, from which 6 were chosen. And I don't care what order they choose the numbers in, as long as my 6 numbers get chosen. So the probability of winning with one ticket is, the denominator is how many different ways you can choose 6 numbers from the 49 numbers. So the denominator is just 49 choose 6. And on my calculator, that's kind of child's play. 49 choose 6, almost 14 million. So there's 14 million ways you can choose 6 of those numbers, and my ticket only has one of those ways, so my probability of winning is about 1 in 14 million. So that's a simple example of how you would use combinations and or permutations to find a simple probability answer.